Am I audible? Okay. Okay, then let's start. So this is week number 7. Sorry, my throat is a little bit bad, but you have to bear it. Week number 7. That was about cross moments and covariation, covariance, variance, etc. Right? And correlation. So overall, the week was about how different random variables can be related to each other. So just like every week, let's start with a quick recap of what was done. So we started with this central moments, right? Central moments of order, arbitrary order, ij, and that is nothing but mu ij defined as expectation of x minus expectation of x to the power I and y minus expectation of y to the power j. Okay. And as we can immediately see, if I put mu 1 comma 1, then it becomes expectation of x minus expectation of x times y minus expectation of y. And this is an important quantity. In fact, so important that it has its own name. It's called covariance, which is a scalar, just a real number of x comma y or between x comma y. All right. And that has some nice property. So covariance of xy is equal to covariance of yx. Then if we have covariance between x and x, that is same as variance of x. And the third was very important. If x and y are independent, then covariance of x and y is 0. Okay. So covariance in some very vague sense is a metric of how correlated they are, how dependent they are. If they are independent, then covariance is 0. The same is true for correlation as well. As we will see, correlation is nothing but covariance normalized by the variance of each random variable. And there was one important thing, which was that covariance of x and y, or rather x plus y, if I want to write, that would be, sorry, variance of x plus y. So variance is not always linear. We would want to write it like variance of x plus variance of y. But in general, it is not true. There is some cross interaction term between these two, right? And that is given by 2 times covariance of x comma y. All right. So you can think of it as some square function, for example. Square of x plus y is square of x plus square of y. Thus, there is 2 times x times y. So this is the cross term, right? Similarly, this covariance is cross term. When we expand the variance function. And now we can see if x and y are independent, then by this property, covariance is 0. So there is no cross term. Then variance becomes linear. So variance of x plus variance of y. Okay. Next, we defined a Yeah, we defined a sigma matrix that is called variance covariance matrix. And the rule that defines this matrix is that ijth entry of this matrix is the covariance of xi and xj, where ij is both are between 1 to n, where n is some predefined number. Okay, so sigma would look like this: variance of x1, then covariance of x1, x2, all the way up to covariance of x1, xn. The same thing goes on, right? So last entry would be covariance between xn and xn, which is nothing but variance of xn. Okay. For example, this entry would be covariance of xn and x1. It is same as this quantity because covariance is symmetric. All right. And to find the covariance between two variables, best way is to find expectation of xy and subtract expectation of x times expectation of y. Okay. So it's similar to expectation of x square minus expectation of x times expectation of x, which is the square of expectation, which was the definition of variance of x. Okay, so you can see the extension here. All right, and there was this one nice property, which is that this sigma is positive semi-definite, which means all the eigenvalues are non-negative, and that means that for any vector x, you have x sigma x transpose greater than or equal to 0. Okay. And in mathematics, when we have some PSD matrix that is positive semi-definite, it enjoys very nice properties, right? Some of like it's a good convex thing, etc. So right now we are not worried about it, but it's important to remember this thing. Okay. So here x is any row vector. Okay, some people define x as a column vector in general. Then it would have been x transpose sigma x. Okay, but just that first should be row, then matrix, and this should be column. Okay, so that the entire thing becomes just one number. So the structure should be row, matrix, and column. Okay, this will give a number. Okay. And we will anyways do one example on this in assignments, how to calculate covariance in this sigma matrix. So let's not worry about this. Then we looked at generating function. So first was probability generating function for multiple variables, that is. So we have x1, x2, etc. up to xn. And we want to find the probability generating function of this. So that would be a function of also n variables, which we call S1 to Sn. And that is given by, if you remember earlier, it was probability of x1, right? Times s to the power x1. But now we have not only x1 but x2 all the way up to xn. So here also we would have s1 to the power x1, s2 to the power s2, and Sn to the power xn, and summed over all possible x1 to xn. Okay, so that's that. And if xi's are independent, then we have a nice property that this will be equal to product of all their independent generating functions. Okay, 1 to n. All right. And there was another property. Again, if they are independent, then the moment generating function of this variable, which is the sum of xi's, x1 to xn. So now this is just one random variable, right? So it has just one variable here as argument, and that is given by product of all the generating function evaluated at the same value, that is this s. Okay, so this is important. Similar thing can be defined for moment generating function mgf. Yeah. It's the expectation of e raised to x times t, where t itself is a vector, right? So t1, t2, etc. So t is t1, t2, all the way up to tn, a row vector of random variables. Sorry, just the real numbers. X is a sequence of random variables. And again, all the properties stay the same. So everything about this also holds for MGF. And there is this characteristic function, which is expectation of e raised to I x t transpose. So instead of x times t transpose, we have an I sitting here. And now we don't have to worry about what should t be. Here there was a condition that the magnitude of t should be bounded, right? So here there is no such condition. And again, all these properties hold. Okay. Next was correlation coefficient. Okay. And there was this bookish definition given in terms of covariance. So this is actually covariance, but the problem with covariance is that it can be unbounded, can be as large as you want, right? But we want a number that defines how correlated two things are. But we need to know that if it is 0.6, it means something. So we need to normalize it by the variance of x square root of and square root of variance of y. Okay. And now this can be shown that it is between -1 to 1. Okay. 1 means perfect correlation. Which means if you tell me the y, I can immediately know what the value of x is up to some constant. And similarly, if rho is -1, then too it's perfect. But instead of correlation, it is anti-correlation. So if we have two variables, let's say, and it's a time series, something like this. And the second one is also same as that, but maybe scaled by some factor. I don't know if this is a good drawing. Okay. So now this is y, and so y is equal to some k times x, where this is x, if where k is positive. If k is negative, then what I get is, if I something like this, then y goes against x. So it would be something like this. Okay. So y is minus kx with k positive. So this is anti-correlation, this is correlation. This is the heart of statistics. The statistics is the heart of any quantitative science that we do, especially the empirical studies. Okay. And as you know, there is a famous saying that correlation does not imply causation. What it means is that it may be that two things are perfectly correlated. So you would think that x is causing y, or x is determining what the value of y is. but that need not be the correct one. For example, you can have a plot of as a function of time. Uh, this is a famous thing, number of ice cream sorts. Okay, and this is like 1 year. And if you look at another variable, which is also like this, and you would ask what that variable is, that is the number of shark attacks. And if you calculate rho, that might be equal to 0.8 or something, very close to perfect correlation. So you might think that sharks are attracted to ice creams, or what is happening? Why is there correlation between ice cream sold and shark attacks? But the reason is that there is a third variable which is not shown here. So this was x and y. Sorry. There was another variable. This was x and y. There was another z variable, which was the time, or rather the season. So what happens is that ice creams are sold when the temperature is high, right? In summers, then more ice creams are sold. Similarly, when there are summers, people go to beach often, especially in the Western countries or high latitude countries. And that's why, because of the time, both these things happen. Shark attacks increase because people go to beach, and ice creams are sold because people like ice creams in hot weather. So this is something that needs to be remembered. This is called a confounding variable or something like that. Okay, name is not important, but just because you have correlation in general, that does not mean causation. If you are interested, there must be a Wikipedia page where there are many such examples. Okay, that aside, some properties of rho. First is that it is symmetric. Correlation between y and x is same as between x and y, and it is always less than 1, less than or equal to 1. So 0.8 correlation means that they are almost correlated but not 100% correlated. Whereas if we just define covariance as our correlation, then that is bad, because covariance could be 300 or 3000, but that does not mean anything. So we normalize it so that we know that 1 means maximum correlation. Okay, it's like probability. And correlation between a variable and the variable itself has to be 1, right? Because x is correlated to x. If you tell me what the value of x is, this second x is also immediately known. Then there is another important thing, which is ax, correlation between ax plus b and y. That is same as correlation between x and y. Okay. And now let's try to understand this, because there will be a question from this. Firstly, when I add b to it, it does not change the correlation. It's just a constant. So correlation is still the same thing. Again, if I multiply x to something, it does not still change anything. Why? Because that will only increase the variance, and it will increase the covariance also by the same amount. So because of this normalization by square root of variance, that factor a will be cancelled out. Okay. And again, if x and y are perfectly correlated, then ax plus b and y will also be perfectly correlated. Okay, so just remember this thing, that the coefficient does not matter and b does not matter as long as a is positive. If a is negative, let's say a is minus x, then you are inverting the function, this function. Okay, so as you know, perfect correlation would go to perfect anti-correlation. So this will become minus rho xy when a is negative. Okay. So all in all, I can write that this is equal to A divided by mod F times rho xy. Okay. And finally, rho xy is equal to 0 if they are independent. Okay. Converse may or may not be true. So in general, not true. But if they are independent, then the correlation would be 0, which is what you expect by the English language also, right? If we are independent, then there should not be any correlation between us. Okay. Finally, before we go to assignments, the last thing that we study was conditional expectation. So I'll just give for the discrete part x given y probability. This is what we had already studied. Probability that x given y, that is a function of both x and y, is probability that x is equal to x given that y is equal to y. Okay, and the inherent assumption is that this probability is not equal to 0. Otherwise, you cannot divide. So conditional expectation is based on this. So expectation of x given that y has some value, small y, is given by sum over x, x, and this probability, x given y of x given y. So as you can see, there is one dummy variable which is being summed over, which is x. So this thing does not depend on x because x is summed over, which means only y remains. So it is important to remember that this is a function of y. Okay, generally expectation is just a number, but this is not expectation. This is conditional expectation. So that is a function of y. Always remember that. Okay. Also called regression of x given y. That's just a name. And in continuous case, this would be equal to integral over x and then conditional distribution of x given y dx minus infinity to infinity. Okay. Again, it's a function of y. All right. So I guess that's about it. And then there were some properties. I don't think it's that relevant. So let's go to assignments. Any questions so far in the discussion? Okay. And let's go to assignments. So the first problem is a big one. Okay. It's very easy, but we have to calculate. So don't get intimidated by it. We just have to work it out. It's not that difficult. Others are not that involved either. Okay, so would anyone like to solve it first? I'll say what it is. So we are given two variables x1 and x2 with joint distribution, and as you can see, these are discrete variables. So x1 can take value 1 or 2, and x2 can take value -1 or 0 or 1. And the joint distribution is given. So probability that x1 is 1 and x2 is -1, that is given by this number, which is 1 over 6. Then x1 is 1 and this is 0, that is given by 2 by 6, etc. So this is given. And we have to find the expectation of x, which is nothing but expectation of x1 and expectation of x2. That's the vector. And this matrix, sigma matrix, right? Variance covariance matrix. So can somebody tell me what to do, how to start? Don't have to solve, just tell me the strategy. Okay, you don't want? Fine, then I'll solve it myself. Okay. So what we want is first expectation of x1. So expectation of any quantity is the integral of x1 times the probability, right? And then we have to integrate. So this is the probability e x1 x2, not integral summation because we are dealing with discrete variables. So x1 and x2. All right. So now I can write for each entry I have to multiply the value of x1 and then the probability. So for the first entry, x1 is 1. So 1 times the probability 1 by 6. Then again for this one, x1 is 1. So 1 times 2 by 6 plus 1 times this value which is 0 plus now x1 is 2. So 2 times 1 by 6, again 2 times 1 by 6 plus 2 times 1 by 6. So we get 3 by 6 plus 6 by 6, which is half plus 1. So 3 by 2. Okay. So this is expectation of x1. Try to do it alongside me. And if you don't understand something, just do not hesitate to ask me. Okay. And if you think I can't listen to you, then type it in the chat box. Now expectation of x2, same thing, sum over all x1, x2, but x2 multiplied by probability x1, x2. So now x1, x2 can take minus 1 value. So for minus 1, we have 1 by 6 plus minus 1 times 1 by 6 plus it can take 0 value for this probability, but that would be 0, right? So 0 times something. And then 1 into this is 0. So 0 plus 1 times this probability 1 by 6. So this turns out to be minus 2 by 6 plus 1 by 6. So 1 by 6. Okay. So our expectations are 3 by 2 and sorry, minus 1 by 6. 3 by 2 and minus 1 by 6. So the only correct option is this one. So this must be correct, but we have to still find sigma matrix. Okay. Now for sigma, we would like variance of x1. This is variance of x2. And this is covariance, right? x1, x2. This is also covariance. So for variance of x1, we need expectation of x1 square also, which is sum over x1 square probability x1, x2, summed over all x1, x2. So again, it's the same thing, this very thing, right? But here the coefficient was x1, so 1, 1, and 1, then 2, 2, 2. Now we have the coefficient x1 square. So we would have 1 square times 1 by 6 plus 1 square times 1 by 6 plus 1 square times 0 and plus 2 squared times 1 by 6, 2 squared 1 by 6 and 2 squared 1 by 6. Okay, so this would be 2 by 6 plus 4 by 2, I guess. No. Just a second. Four by 6 times 3, right? So it is 2, 1 by 3 plus 2. Is it correct? I think I made a mistake. Just give me a moment. X1 square. So it is 1 times 1 by 6. 1 times 2 by 6. This was 2 by 6. Yeah. So this is 3 by 6. This would be 1 by 2. Okay. So this would be 5 by 2. Yeah. Similarly, expectation of x2 square. So this means, by the way, variance of x1 is expectation of x1 square, which is 5 by 2, minus square of the expectation of x1, which is the square of 3 by 2, 9 by 4. So this would be 5 4s are 20 minus 9 2s are 18. So 2 by 8 or 1 by 4. Similarly, expectation of x2 squared. So now these numbers are squared, right? So everything becomes plus 1. So you just get 1 times 1 by 6 plus 1 by 6 plus 1 by 6, which is 1 by 2. So just 1 by 2, which means variance of x2 is 1 by 2 minus expectation of x2 cos square. So 1 by 6 squared. So 1 by 2 minus 1 by 36. So I have to multiply 18. So this becomes 17 by 36. Okay, so variance are known. So we know these two things. Now we need to know covariance of x1, x2. So covariance is given by expectation of x1, x2 minus expectation of x1 and expectation of x2. So those two quantities are already known, which means we already only have to calculate expectation of x1, x2. Again, expectation of any quantity is that quantity multiplied by the probability. Okay, so now we have to know distribution of x1, x2. Sorry. So if x1 is 1 and this is minus 1, then in bracket I'm writing x1, x2. Okay, in bracket is x1, x2. This would be minus 1, this is 0, this product is 1. Then 2 times minus 1, that is minus 2. This is 0 and this is plus 2. Okay. So these brackets are denoting x1, x2. So now we have to multiply all these numbers together and add them up. So the first number is minus 1 by 6. And the second is 0 times 2 by 6. Then 1 times 0 minus 2 by 6. Then 0 and 2 by 6. Right? Yeah. So these two get cancelled. We have 2 by 6 minus 1 by 6. So just 1 by 6. Which means covariance is 1 by 6 minus expectation of x1 times expectation of x2. So these two quantities, 3 by 2 and minus 1 by 6. 3 by 2 and minus 1 by 6. So in 1 by 6 plus 3 by 6 is 1 by 2. So 1 by 4. 10 by 24, which is 5 by 12. So the sigma matrix is variance of x1, which is 1 by 4, and variance of x2, 17 by 36, and covariance on the off diagonal terms. Covariance we calculated 5 by 12. Okay, so this is the answer. Is everything clear? Because this kind of questions are very probable to come in exams also. Okay, so let's just match once. 1 by 4, 17 by 36, 1 by 4, 17 by 36, and 1 by 12, 1 by 12. Sorry, is it 1 by 12 or 5 by 12? Oh, it's 1 by 12. Made a mistake then. Sorry, this is minus. This is minus, so this is minus, minus. And this would be 2 by 24, which is 1 by 12. Okay. So 1 by 12, 1 by 12. Okay, so as you can see, it's very much likely that you will make mistakes. Okay, second one is easier. That is that we don't have to do that much work. So the question is that joint PDF is given. So now we have a continuous distribution in the first quadrant, which is given by this exponential e raised to minus x plus y. We have to find the expectation of this quantity. And again, expectation of any quantity is just the integral of that quantity multiplied by the probability. From minus infinity to infinity, minus infinity to infinity. This is the general definition. But we know that it's non-zero only in the first quadrant. So it becomes 0 to infinity, 0 to infinity, xy. Fxy is e raised to minus x, e raised to minus y, dx, dy. Okay, now we have to see two things. First is that these limits don't depend on xy, and that this function can be broken or split into function of x and function of y. Correct. So this is just x part and this is y part. So this is split. This is not always true, but in this case it can be split. So we will make use of this. So I can write 0 to infinity x e raised to minus x dx. And then the y part 0 to y e raised to minus y dy. Okay. As you can see, both the integrals are equal. X and y are just dummy variable. And we know that 0 to infinity x raised to n e raised to minus x dx. This is the definition of gamma n plus 1. And for integer n, this is n factorial. So here we have x raised to 1 and y raised to 1. This is just 1 factorial times 1 factorial, which is just 1. Okay. So the answer is 1. And why would we even calculate expectation of xy? Because we want to calculate covariance, right? It's not asked in this question, but if you want to calculate covariance, this is the first thing that we need to calculate. And then expectation of x and expectation of y. And we know that because this can be split into two functions, it means they are independent. So the covariance would be 0. And in fact, you can show that the expectation of x is also 1, expectation of y is also 1, right? Because this is exponential of minus x, and exponential of minus y. And we know that this is lambda, right? Lambda is equal to 1. And the average of this is 1 by lambda, which is 1. This also, the expectation is 1. All right. So this means that covariance would be 0. So would be the correlation. Okay. The third question. Now two variables are given, x and y. We are not even told whether they are discrete or not, because that is not needed. Variance of x and variance of y are given to be sigma square. So you would think that they are IID, except that they are not, because then the covariance would be 0. But covariance is some non-zero quantity, sigma square by 2. And we have to find the correlation between not just x and y, but 2x plus 3 and 2y minus 3. Okay. So rho 2x plus 3, comma 2y minus 3. And now we have to remember those two things. First is that, oops, yeah. First thing is that this minus 3 plus 3 does not matter. Because if you shift your signal or random variables, that does not change correlation. This means this is equal to rho 2x and 2y. Okay. Then we know that rho 2x, let's treat this 2y as some other variable, 2y. Then 2x does not change the correlation because this is given by 2 divided by mod 2. Okay. So just the sign of 2, which is positive. So correlation stays the same. Let me just keep it that way. And now 2y, we can do the same thing. 2 divided by mod 2. So x comma y. Okay. This is obviously 1, 1. So this is rho x comma y. Now this is very easy to calculate. By definition, this is covariance divided by square root of variance, square root of variance. And if you want to write, you can write x, y. So covariance is given sigma square by 2. Variance is sigma square. So square root is sigma and sigma, which is 1 by 2. Okay. Great. So the answer is 1 by 2. There is 50% correlation between these two variables because there is 50% correlation between x and y. Okay. Yeah. Now a similar question. So the argument is same. What is given is that x and y with variance sigma square and covariance sigma square by 2. We have to find variance of this number. So earlier it was covariance between 2x and 3y or some scaled variables, but now it is variance of these two things. So let me just write it down, 2x minus 3y. So this is variance of, first let me write 2x plus something, where something is minus 3y. Okay. And variance is linear, so that we can write variance of 2x plus variance of 3y minus 3y, except that we know that variance is not always linear and there could be cross term. In fact, there is, which is this covariance, right? But it is covariance between 2x and minus 3y. Okay. Just a second. Yeah. So variance of 2x, we know that this becomes square of 2 times variance of x. And variance of minus 3y, that is minus 3 square variance of y. And this becomes 2 times this coefficients come out. So 2 and minus 3 times covariance of xy. Okay. This is covariance. Okay. If it was correlation, then this 2 and minus 3 won't come out. They will just disappear. It's just that minus 3 will pick up a negative sign outside. Okay. Now it's easy. 4 times variance of x, which is sigma square, plus 9 times sigma square, minus 12 times covariance of xy, which is sigma square by 2. This is 4 plus 9 minus 6 sigma square. 4 plus 9 is 13 minus 6. This is 7 sigma square. So the answer is 7 sigma square. Okay. Any questions or everything is clear? I hope it is clear. If not, then you can always ask me anytime. Okay, just interrupt me. Okay, this one is also a very straightforward question. We are given two random variables, x and y, and the PGF, probability generating functions, are given. First is whatever it is, does not matter. Second is again whatever it is. And most importantly, it is given that they are independent. Okay. So we have to find the PGF of x plus y. And this was in the notes. So PGF of x plus y, which is some function of t, right, can be written as gx of t times gy of t. In bracket, because they are independent. Okay, so this India-Pakistan condition, that is that x and y are independent, that is given. That's why we can write it as this. Before 1947, we could not write like this. Now it's just multiplication of these two things. So coefficient is 1 by 3. This is 1 plus 2t plus 3t square whole square times t plus t square. Yeah, and that is the answer. So I guess the first one. Yeah. Okay. So it was literally multiplying this two. That was the answer. Again, we have to find moment generating function. So x1 and x2 are given to be IID, random variable having standard normal distribution, which means mean is 0 and variance is 1. And this another random variable is defined in terms of x1 and x2, which is x1 squared plus x2 squared. And we have to find the moment generating function of c. So z is only one-dimensional random variable, so it has just one argument t. Okay. So what we are given is that x1 is normal with 0 mean and 1 standard deviation or variance, and so is x2. Okay. And very importantly, they are independent. So z is x1 square plus x2 square, but x1 square and x2 square are also IID, right? Because these are just square of the normal random variables, so Gaussian. But square of Gaussian is whatever it is. So both of them are again identical and they are independent. So I can first write gz of t as gx1 square of t times gx2 square of t. They are independent. But both of them are identical also. So I can just write both of them are going to be equal. Square of gx1 square of t. So all we need to do is find this. So gx1 square of t would be, by definition, expectation of e raised to tx1 square, right? Which is nothing but integral from minus infinity to infinity, e raised to tx1 square and fx1 dx, where fx is, so I'll drop the x sign, the 1 index, sorry. So fx is 1 by square root of 2 pi sigma square, but sigma is 1, e raised to minus x square by 2. this becomes minus infinity to infinity e raised to tx square 1 by root 2 pi outside and e raised to minus what? Minus x square by 2 dx. Okay, now we have to just integrate this. So first let me convert it into Gaussian curve. So e raised to minus x square times something. And that something would be 1 by 2 plus t, or rather minus t, right? So in fact, let me write it as, I'll keep the 2 outside. So this becomes 1 minus 2t dx. Okay. So side note, this is called Gaussian curve. So minus infinity to infinity e raised to minus ax square dx. This is a very well-known result that turns out to be square root of pi by a. You might have done this in one of your courses. If you have not, then I can prove it for you. We'll do that later if we have time. Okay, but this is called Gaussian integral. So now we can use directly this result. This is how, by the way, we get this square root of 2 pi sigma square normalization factor, right? So 1 by square root of 2 pi, and this is equal to square root of pi divided by whatever is sitting in front of x square, right? Is a. So in front of x square, what is sitting is 1 minus 2t divided by 2. So 1 minus 2t whole divided by 2. So 2 gets above. This 2 pi gets cancelled, and I am left with square root of 1 minus 2t. So this was gx1 squared t. And our answer was square of this number, which means gz of t would be 1 by 1 minus 2t. Okay. And clearly, for this to make sense, t has to be less than half, right? Which means here also t has to be less than half. So it is 1 divided by 1 minus 2t. Option B. Alright. Does everyone understand this? Okay. And the seventh one, I don't know why it is there, because it was already done in the class. But even to summarize, x and y are independent Poisson distributed random variables with different parameters, lambda 1 and lambda 2. We have to find the expected value of x given that x plus y is equal to n. Okay, where n is some fixed integer. So we know that this distribution x given that x plus y equal to n, this follows binomial distribution with parameter n and lambda 1 by lambda 1 plus lambda 2. I think this was one of the previous exercise. Let me see if I can find it. Yeah, this one, right? So this is assignment 6, question 10, where we found that exactly this problem has binomial distribution with parameter n and lambda 1 by lambda 1 plus 2. Okay, so let me just write it down. Week 6, question 10. So expectation of binomial of n and p. This was also done in the class. It is just n times p. Right? You can easily calculate this, but yeah. So this is n times p, which means expectation of x given x plus y is equal to n is just the product of these two numbers n times lambda 1 by lambda 1 plus lambda 2. So the first option. Okay. This was described by professor also in this week's content, so I don't know why it is there, but anyways, moving on. Next question. Again, this is just definition. So x and y are random variables, and the joint moment of order 1 1 of the vector around this value. So by definition, this joint moment of order 1 comma 1 is expectation of x minus expectation of x to the power whatever the first number is, which is 1, and y minus expectation of y raised to second index, which is also 1. Sorry. So this is expectation of x minus ex and y minus ey. This is by definition covariance of xy. Right? So the correct answer is option 2, covariance. Okay. This is the only tricky one in the cohort. So it is given that this conditional expectation of y given x is a plus b times x. Remember, this is a distribution, rather a random variable, which is a function of x. Okay. So this could be of form a plus bx, where a and b are constant, which are to be determined, and that's the only information that is given. So I think it's a nice question. Let's try to solve it. And the idea is given expectation of y given x is a plus bx. Now this is a random variable, which means I can take expectation both sides. A plus bx. Okay. This we know that this is equal to expectation of y. Why? Because that was one of the properties, and you can derive it yourself. I think it was done in the class. And expectation of a plus bx, a is just a constant. So a plus b times expectation of x. So this is the first equation. So now we cannot determine a and b just from this, right? Because we have two unknown. So we have to use another property, which is that expectation of x times expectation of y given x. So this is something that is a function of x. Right? So this will be just expectation of xy. All right. And this can also be written as expectation of x times expectation of y given x. The conditional expectation was given as a plus bx. So x times a plus bx. So expectation of xy is equal to expectation of ax plus bx square, which is a times expectation of x plus b times expectation of x square. This is equation number 2. So now we have two unknown and two equations. So we should be able to identify a and b in terms of these expectations. So let's do that. So I want expectation a to be removed. So let me multiply 1 by expectation of x. So I get expectation of x times expectation of y is equal to a expectation of x plus b expectation of x times expectation of x, which is the square of expectation. And the second equation was just this. Okay, now we can subtract both the sides. So I get expectation of x times expectation of y minus expectation of xy. That is nothing but covariance of xy, but with a negative sign. And here we have expect b times expectation of x whole square minus expectation of x square. So again, negative of variance of x. I hope it is clear. If it's not, then ask me. I'm just subtracting and using the formula of covariance and variance. So b is covariance of xy divided by variance of x. And now I can put this value of b in the one of the equation. I think the first one is easy. So a is equal to expectation of y minus b times expectation of x. Right? Yeah. So expectation of y minus b is this thing. So covariance of xy divided by variance of x times expectation of x. And I don't think this can be simplified a lot. And in fact, that is what is given in the option, right? So a is expectation of y minus covariance divided by variance times expectation of x. And b is covariance divided by variance of x. So a and b are the correct ones. Okay, so the idea was to use these two properties, this one and this one. Once you have that, then it's just proper algebra, which I think all of you can do it. Okay. Now the last question. And what it says is that we are given a uniformly distributed random variable from 0 to 1. So its distribution is just 1, between 0 to 1. And there is another variable, which is y, which is chosen from 0 to x. And the PDF, which would be now conditional, is probability or the distribution of y given x is 1 over x if y is between 0 to x and 0 otherwise. Okay, so let's just draw where the plot is. So where the distribution lies. So 0 to 1, that is the x. This is the line y is equal to x, right? So y can at most be x, which means it has to be in this region up to 1, because x cannot be more than 1. So in this region, we have the probability defined. And what is asked is expectation of y raised to k. So again, y is, we don't know the distribution of y. If we knew the distribution of y, then this question is very easy. But we know the conditional distribution of y. So we can find the conditional distribution of y raised to k given x. And then we can take once again expectation, because this by definition, or not definition, but we saw the property, this is expectation of this variable, which is y raised to k. And this can be written as expectation of y raised to k given x, that is integral of y raised to k, then distribution of y given x, which is 1 over x, and integral over y, and y could only go from 0 to x. Okay. So this is equal to, now 1 by x can be taken outside. Yeah, so 1 by x can be taken outside, and y raised to k integral is y raised to k plus 1 divided by k plus 1 from 0 to x. This is expectation of 1 by x raised to k plus 1 by k plus 1. Expectation of x raised to k divided by k plus 1, which is nothing but integral of this number x raised to k divided by k plus 1, this function, multiplied by fx dx, 0 to 1, and fx is equal to 1 divided by 1 minus 0, right? Which is just 1. Why? Because it was uniform. Which means this is equal to x raised to k plus 1 divided by k plus 1 whole square from 0 to 1, which is nothing but 1 divided by k plus 1 whole square. Okay. So the answer is the second one. Again, not very difficult, but we have to remember this property. Why? Because we are asked expectation of some variable, but the distribution of that variable is not given. What is given is that distribution of that variable given the value of x, so the conditional distribution. So we can only find the conditional expectation first. But then we know that expectation of conditional expectation gives us the final expectation value, which is what is asked. So this property is very important. Once you know that, the rest is just calculus. Okay. Any questions in that? In any question? No question? At least tell me there are no questions. Akshay, are there any questions? Okay. If not, then let's call it a day. I think everything was very clear, surprisingly. But yeah, okay, then let's meet next week. No, sir. Okay, thank you for the response. Yeah, at least I know that you are listening. Good. Yeah, so as I was saying, if there are no questions, then let's meet next week. We are slowly moving towards statistics, and it will be a fun ride. We are officially into the second half of the course, right? So, okay, let's meet next week. See you, everyone. Bye bye. Have fun. Thank you. Yeah, thank you, Usha. Bye.